Thanks for coming. I just want to say one thing. We're here in Bangkok. I had the opportunity in sort of the 2017 to 2020 era to do a bunch of work here in Bangkok with the engineering team and with the regulators. We had a regulated digital asset company. And if you have the chance to engage with folks, people who are coming here from other parts of the world, really strong community here, a lot of really brilliant engineers. I think some of the world thinks of Thailand as a place to go on vacation, but this is a place full of builders. You can look out the window and see that they probably added 400,000 apartments in the last year or something, and a lot of stuff is happening technically too, so don't miss that. Anyway, so I'm here to talk about the how and why of verifiable AI, which is what we do at EZKL. And I'm going to talk about two stages. Stage one is kind of data. How do we analyze data? Big data statistics. And so I have some questions for us to meditate on. One is, does data matter for your business, right? Do you have to make decisions based on data? Does data matter for your protocol? Maybe you're not comfortable saying what you're doing as a business and it's a protocol. Okay, well, we still need those things to work. And not only do they have to work, they have to grow, right? So I think that data mattering, analyzing data in terms of growth is about, I'm talking to someone else, I'm trying to sell someone something, I'm trying to make an execution happen that is what I promised, and then to do any of that, I need to convince someone else that the data that I'm using is correct, like Mo was talking about, and that the analysis that I've done on it is correct. And if you do care about data, how do you use data today? So, I don't know, has anyone used Python in the audience? Yeah, okay, good. So maybe you play with AI, PyTorch, probably a little bit fewer. If you do I used to teach statistics, so maybe we use R, and SQL. Maybe you use big data packages, Spark, Snowflake. A lot of people use Python, especially with AI, and so that's kind of one of the main places that we focus. Oops, wrong direction. And so as you probably guessed, I'm getting at the question of like, does it data matter? And does it matter if you can convince someone else inside your organization or in another organization, a counterparty? You're trying to sell them a package of securities and they want to know, are the loans in this package any good? All of these, you want someone to believe your financial statements, right? So all of these things are a requirement that someone else believes that the data is actually real. And of course, today we rely on trust to convince others. We rely on audits. We rely on staking your freedom, right? It was fraud. If you commit a fraud, then you go to jail, right? And of course, with everything we're doing in blockchain and in ZK, we're trying to replace trust with verifiability, right? So this era of relying on trust to convince people that the data and the analysis is correct is over. And so the question I really want you to think about is, what if you didn't have to do that, right? What if you can always prove to everyone else that the analysis that you did on the data is correct? What does it unlock? What sales can you make that you weren't able to make before? And so, of course, this is the inspiration for what we're working on. So we decided to focus on kind of PyTorch and TensorFlow, traditional statistics like time series analysis, things like decision trees, XGBoost, all the models that are kind of the low-hanging fruit and that are widely deployed to make those decisions today. And you can work with them in Python notebooks. And what we do is kind of create proof mode. So you have a bunch of Python code, you've tuned it, your quants built some stuff, and now we can sort of turn on proof mode for that, right? Make all of that analysis that you did verifiable and verifiable on-chain. So you take your algorithm expressed in Python, you compile it with EZKL down to a zero-knowledge proof, or prover, verifier pair, and then you can input confidential data, public data, all of the inputs, and you get out some public output and the proof, the certificate that what you did is what you claimed you did. And then that can be verified on browsers. In browsers, I'll give an example of course, on blockchain with smart contracts, but even also small devices, maybe a counterparty, maybe a regulator. And these proofs happen everywhere too. So we now have the ability to prove on a Raspberry Pi. We have an iOS package, so you can write an iOS app that can do proofs if you want to use it on your phone or a Vision Pro or whatever it is. And of course on computers and on servers and on proof networks. One of the things we did using this was this Optimism Retro PGF funding. So, Optimism gives away money or gives away not money, but Optimism tokens as a reward for participating in the system. And it's important to secure something like that because there's a lot of money at stake, right? Voting in general is something we want to be verifiable. And so they had implemented their algorithm as a Python notebook. So we were able to take that Python notebook, convert it into a prover and verifier pair, and show that all the ballots were correctly counted, and the allocation algorithm was done correctly. And then you can verify. Anyone can go to the website and verify that it was what we claimed. So another big application of this is decentralized AI networks. A number of decentralized AI networks have started to use EZKL in their system. And so what happens is participants or sponsors create an artifact, distribute the proving artifacts and the verifier artifacts. The miners or the validators of some kind make a request. The miners compute it and return the proof. And some of the networks that are using it today are like Inference Labs, Ritual, Open Gradient, and a bunch of others that are somewhere in their development cycle. But already we've seen kind of up to 1 million EZKL proofs a day computed in these networks, deployed on thousands of nodes. So this is something that's like actually out there in production doing decentralized AI. And we expect that to continue to grow because there's a lot of interest of other folks that would like to integrate it. Okay, so then I think one of the other things that we're going to see is DeFi. So I kind of think of this as we're entering an eternal summer of DeFi, right? So there was a lot of innovation. Some of the innovation slows down. Part of the reason innovation slows down is because getting complex algorithms into Solidity is not that easy, and you need like some other indirection solution, crypto economics. But with this kind of technology, what you can do is you can take existing battle-tested models that live in notebooks, instantly turn them into something that can be executed on chain. And one of the biggest focuses for our users today, a number of different groups, is kind of making AMM smarter. So taking an AMM and letting it do Markowitz mean variance optimization or some other portfolio construction algorithm for its trade acceptance function. And on the other hand, building strategy vaults, where this vault is running the same algorithm all the time. It's a complex algorithm that uses existing like time series and historical data and everything else. And in some sense, these things will probably eventually merge into the same type of object. What else? Okay, so the basic package that we provide, most of what I've been talking about today is the research phase. So during the research phase, fast iteration with Python notebooks. We do have a hosted proving environment that you can use for giant experiments. And let us know if you want to use that. Really broad model coverage, so most of the time your model will work without talking to us. If it doesn't, you can talk to us and we'll make it work. And lots of examples, texts, test docs, and templates. And then we get into a build phase where you might want more custom engineering, performance tuning, and in production, as we've seen with the DAI networks, sometimes it's nice to have dedicated clusters, as well as be able to take that Python notebook and pass it on to your end users. Stage 2. Okay, so that was our standard data sales. Now I'm going to say some crazy stuff about AI. So if you weren't paying attention, we're gonna have a little bit of fun now. Okay, so this is about coordinating with AI. So there's this kind of AI safety thing, which I think a stylized version of that is, hey, we created a new intelligence. What's the first thing we want to do? Make it do exactly what we want. And I find that kind of, the Star Trek fan in me is like, that's not how we should treat a new intelligence, right? Like, we need to coordinate with that intelligence, not just dominate that intelligence. So this is kind of about how could we use this kind of stuff to coordinate with AI? Okay, so people coordinate, right? People coordinate pretty well. And when we coordinate, emotions are a big part of what we do, right? So we get angry at the outgroup, at the aggressor. We look to punish them. We feel love and loyalty for our partners, for our team, our community. And that loyalty gets into the irrational level, right? We make things that are short-term sort of bad for us. In order to do that, we feel guilt, sadness, arousal, disgust, all kinds of emotions that affect our judgment and behavior. And we want AIs to coordinate. We want to cooperate with them. So let's think about kind of how emotions work. So another thing is like, this is sort of an anti-AI piece of propaganda that you may have seen. It's like, oh, this thing is this horrible monster, and then there's like this cherry on top that makes it look friendly. And why is that good propaganda? Of course, it does trigger disgust and motivate sort of attack and squash this thing. But it also really what it's communicating here is the deception, right? The AI's commitment, its promise to do things in the future is not credible, right? Behind it is this monster. So our AI is untrustable. It's sort of, it can promise to coordinate and then immediately defect, immediately cheat. It can say, oh, I'll be on your side and I'll fight, and then it can immediately give up. Its emotions are sort of skin deep, you know? It's a deceiver. It doesn't really feel them. It's just parroting them. It's a stochastic parrot, right? And that makes us uncomfortable. Why does it make us uncomfortable? I mean, how can we make this thing into our friend? What's the normal way of interacting that we feel is being betrayed here? Like, and how do we get over this risk with each other? How can we use that to trust AI? And that kind of leads to the question of why do we have emotions, right? So why, or more precisely, like why would we have evolved emotions? And one sort of theory of this from the evolutionary psychology literature is that emotions are mechanisms to coordinate the activity of other programs that we're running. Right? The program superficially does some stuff, but it's not well coordinated towards some goal. And what's happening, so the emotion causes a framing, right? It says, I'm angry, I see everyone is against me, I'm ready to fight, right? It helps you to prioritize what your next action is going to be. Right? I have a lot of adrenaline. It gives you a perceptual filter. You know, all the actions that you see or all things in the world, you filter them through the lens of the emotion that you're feeling. And so these two things kind of control create a commitment to your future actions, and they're visible and hard to fake. So other people can see that I'm feeling angry or or I'm feeling loyal, or I'm feeling embarrassed or whatever, right? So they're hard to fake. And then all those things together mean that they become an effective commitment mechanism in a two-stage game. What do I mean by that? Two-stage game, so one example is a mugger, right? A mugger says, give me your wallet or I'm gonna stab you, right? And if I give them the mugger to the wallet, yeah, okay, they're not going to stab me. That's the best outcome. But if I don't give it to the mugger, it's actually worse for the mugger to stab me, right? Because then they might go to jail, right? So therefore, if I know that's going to happen as the owner of the wallet, I should just say no, because the mugger is going to back down, right? So the mugger, what they have to do is create a credible threat. I'm crazy, you know, I'm going to stab you. I'm going to go through with the threat. Right? Or I'm so angry, I'm going to go through with the threat. So they have to make this commitment in the two-stage game in order to get me to believe and to get to their better outcome. On the other side, something more positive. Okay, why do we cry? People have asked this question. One theory is that it's kind of a sincere request for an alliance. It's hard to fake unless you're a trained actor. It says, you know, my bloodstream is full of oxytocin. I'm open to bonding. I'm showing vulnerability and promising you loyalty in the future, right? That's one theory of why we do it. Okay, so what does it have to do with making an alien intelligence into our friend, right? Okay, well, so let's look at a historical example, right? So here was this alien intelligence, came to our campfire, it became our friend, right? And what kind of a stylized version of what's happening here is it was a two-stage game. The human is deciding, do I feed the dog or not? Do I feed the wolf or not? And then the dog is deciding, okay, if there's a threat, let's say, is it going to defend? Is it going to be a watchdog? Even if defending may cost it its life, right? If you care for me, I'll die for you. And we created this bond, right? We made this alien intelligence, our friend, and we feel confident. We know that this thing is not a deceiver. We believe that it will keep its side of the deal, right? The dog. How did it do that, right? It did that partly by this, right? By kind of showing how it feels through its emotion, and then us believing that that kind of emotion is connected to how it will actually behave in the future. And so this is this paper by Kaminsky and others that said, what happened was, you know, here's the wolf and here's the dog, and over 30,000 years, the wolf evolved new facial muscles so that it could make puppy dog eyes and show us that it was going to be loyal in the future, right? So that took a long time to implement, and you know, with the pace of AI development, we don't have 30,000 years, right? So we need some other way for the AI to convince us that it's going to do what it says it does. But of course, AI doesn't have real emotions. It doesn't have an endocrine system. So how can it commit? Okay, so it turns out that in this particular case, the commitment in the sense of a two-stage game and the commitment in the sense of cryptographic commitment are actually related concepts, okay? Or one can be applied to the other. So the theory is we do the same thing that we were talking about before. We compile the model down to a zero-knowledge proof. We can create a commitment to the model, and then I know in the future how the model will behave, right? The model can create, a committed model has a framing for how it perceives the world, a perceptual filter, a set of priorities. It's visible and hard to fake because it's hard to fake a cryptographic commitment. And therefore, it's an effective mechanism for coordination or a commitment mechanism in two-stage games. So it's a way for a model to commit to a future mental state. It's a way for a model to convince you to create loyalty. We just deploy a verifier, we commit to the input, and then the execution of the model itself comes with this certificate. It says, only if it has this certificate should I trust this behavior. Or a better way to think about it maybe is if I'm going to let the AI control a robot, humanoid robot, you put the verifier on the robot so that only the model which is committed to its future actions can control the actuator, can make the decisions. How are we doing on time, by the way? Okay. And the cool thing about this is that there's a lot of situations where we play with decentralized AI and we're worried about, okay, if the thing has keys that can spend money or, drop a bomb or whatever, then we need somebody to hold the keys for the model. Of course, if we're proving the model, there's no separate signature. You don't need keys. It doesn't need keys. The model itself, the execution of the model itself, when it's proved, is the key, right? It's self-signing. Okay, so now I go back to the details of what we've got. And why this is sort of fun. So already, as I mentioned, most of the models, they work right away. So you can go experiment with this kind of idea if you want to, or the straightforward data idea. When everything works with notebooks, so you don't even need to download anything. You can just use Google Colab or another notebook service. Lots of examples and documentation. I mentioned that we have JavaScript, iOS, NVIDIA, Raspberry Pis if you want to connect it to a little robot on something small. And we have a bunch of functional open source demo apps that you can play with. So I'm going to wrap up. It's also very fast. So our proving overhead is now about, in some cases, less than 30 times witness generation. And so there's this kind of perception that ZK is slow, but it's really getting faster very rapidly. This is just this year, not even to today. We've got some more recent improvements on a MacBook. Our target for things like DeFi proofs is actually milliseconds, or not like maybe hundreds of milliseconds. So like our target is L2 block time. Right? So you should be able to compute a proof within a single block of an L2, not wait an hour. Okay, so I have two asks for you. One is, play with it, run some models, see if it works or not for you. All the tooling is ready, used in production, and proof times are falling rapidly. They're falling faster than GPUs get faster, so eventually we'll catch up and we can run anything we want. And two, just want to let you know that we're hiring, particularly on the business side and on DevOps. So that's all. Thank you.